Hello, my name is Andy Schweitzer, and this is a video highlighting the how to balance and write out oxidation reduction reactions. A couple topics that we'll look at in this topic, more detail at least, would be how to write out a redox reaction. This is going to include both molecular, ionic, and net ionic reactions. We'll look at calculating the voltage of a reaction. We'll see how that works. We'll assess the question of whether it's going to be spontaneous, or are we going to have to drive this reaction on our own. And finally, a quick look at balancing. And this will only be balancing for what I refer to as simple redox. I'll have another little quick video on balancing complicated, what I call complex redox reactions. They're not complicated, just a matter of being more involved. So more rules to follow. So either way, how to write out a redox reaction. A redox reaction, you could be given a problem where you need to complete the products or what have you, but for this situation, keeping it kind of as simple as we can, we could have zinc, let's say zinc metal, reacting with, let's say, a solution of copper ions. Now, for this situation, we have zinc metal, we have zinc 2+ ions, we have copper metal, and we have copper 2+ ions. These are all the players. These two can switch back and forth, and these two can switch back and forth. The way I would physically run this reaction is I would simply take a piece of a beaker or a well plate of some sort, and I'd have in solution, and I would take and drop a piece of metal in. Anytime that you are charged, okay, this one and this one, they are aqueous. Water is a polar compound, and therefore these things will easily dissolve in solution. When it loses its charge, these two individuals will in fact be solid. If in their normal elemental state they would be a liquid, well then it would be a liquid. If in their normal elemental state it would be a gas, well then it would be gaseous. But at this point it would in fact be solid for those two individuals. So my options here are to have a solid piece of zinc right here and have the copper 2+ ions in the solution. In this case, my reaction would be the zinc metal would exchange electrons and become zinc 2+. The other half of the reaction would be for the copper 2+ ions to exchange electrons and become copper metal. This is a pretty common notation for showing that particular reaction. And the drawing isn't easy to do, but essentially this would come up right here and it would grab 2 electrons. As it grabs electrons, it forms solid copper metal. This would be copper metal, and that would plate the outside. And then as it does that, the zinc would jump off into solution. And we'll put zinc 2+ here. Alright, so that's one option. The other option would be the reverse. I have this same beaker, a little more depth to it, solution, piece of metal. In this case, the piece of metal would be copper, and the zinc 2+ would be in solution. As this thing comes up, it would become solid and zinc metal, and the copper would jump off, Cu+2. I chose +2 because it's the most common copper ion to form. Copper +1 could happen as well. This would be represented by before and after would be copper metal going to copper 2+, and then we have zinc, double line there, zinc 2+, going to zinc metal. So for these two reactions, which one is actually going to occur? This reaction right here would be represented by zinc, no charge, plus copper 2+, yields zinc 2+ plus copper metal. And this guy would be copper, no charge, plus zinc 2+ yields copper 2+ plus copper, back that up 1 second, would be zinc metal. They are the reverse of each other, so one of them is going to be spontaneous and one of them is not. They will have the exact opposite voltages. So for example, let's run through the half fractions here. This is going to be zinc metal goes to zinc 2+, and here are 2 electrons that it's going to be losing, so this is therefore oxidation. And then we have the copper 2+ plus 2 electrons yields copper metal. This for gaining electrons would be reduction. At this point, because the electrons are balanced, these two half fractions happen at 1-to-1 ratios, and therefore this is also my overall balanced equation. We want to gather the voltages off of these two individuals. Now, the voltages you will find from an external data source, what the voltages are. Now, the voltages represent how much an atom is willing to gain or lose an electron. This exchange takes place where one atom is getting rid of an electron and one atom is picking it up. Either process is going to be gaining or losing energy in order to make this process happen. So losing energy is generally considered spontaneous or favorable. So a positive voltage, I often make a smiley face showing this is something that's going to occur. As it occurs, it releases energy, therefore ready to go. A negative voltage is one I often use a frowny face, meaning that it needs to absorb energy in order for it to run, or it's not going to run on its own. It's like a ball rolling up a hill. It will run, you just need to push it all the way. So a negative reaction can run as long as the overall net difference is positive, meaning that if this guy would like to pick up the electron, that's fine. If this guy doesn't want to get rid of it, he'll just needs to provide enough energy to push it along. So we simply add these two voltages together. So in this case, I have a chart here that you will be provided, and there are more in-depth charts, but this is called a reductions potential chart. A few things you'll want to note about this chart. One, it's a relative scale, so hydrogen is essentially 0, and everything is based off relative to hydrogen. So can you figure out how much actual energy it requires to gain the electrons? It's difficult. So they do a relative scale here based off hydrogen. Okay, and it's only reductions. So in this thing, we would find that this one will be as is on the chart. The copper 2+ plus 2 electrons, and right here, exactly as is. Therefore, my voltage is positive 0.34 volts. All right, and then I'm going to go ahead and put a positive 0.34 volts. So it's energetically favorable for copper to pick up 2 electrons to form copper metal due to the positive. And the other one is not going to be on, but it's going to be reversed. So we have looking for the zinc here, and there it is. Zinc plus 2 electrons yields zinc metal. Now this is a negative, but it's also the reverse reaction. Okay. In this case, it's going to be, because it's the reverse reaction, we flip the sign to a positive 0.76 volts. Very important. The oxidation is going to get flipped. Whenever you're checking voltages, one of them is always going to get flipped. Now this gives me a positive 1.1 volts. meaning that this reaction is going to run. So that's this picture right here. So as I take copper solution, put a stick of zinc into it, this reaction will run all on its own because of the positive voltage. The net products would be zinc 2 plus ions and copper metal. So therefore, if I were to take a beaker and put it into it, this zinc 2 plus ions and copper, these are the products of this reaction. The reverse reaction here, okay? These are the products of this reaction. So there's no real reason for this thing to turn around and go back towards the reactants. That's non-spontaneous. This reaction will give me a voltage of 1.1 volts, but the reverse reaction, which is going to be zinc 2 plus copper metal, that's this bottom picture, yielding zinc metal plus copper 2 plus ions. Again, it would have half reactions. It would have a negative 0.76 volts and a negative 0.34 volts, giving me a negative 1.1 voltage. Now, can this reaction occur? Yes. We just need to drive it all the way using energy. It would be the reverse of sliding down a hill. We can always go back up the hill. We just need to provide energy all the way along. This would be an example of maybe a battery that would be discharging in this direction, and we'd have to recharge it with energy to drive it back, and then of course it can discharge again. For this overall reaction, the positive one, there is an anion that's present somewhere, wherever the cation, there's an anion. So we're going to have a total of a negative 2 charge here someplace. So when I write out my reactions, I'm just going to write out the full reaction for this guy here down below. Let's just make a new box here. It would be zinc metal. Okay, so we have the zinc metal plus, let's just say, copper, and let's just say nitrate is our anion. It would look like this. Goes to zinc nitrate plus copper metal. This would be a spontaneous reaction. This is called the molecular equation. It's holding things together when in reality they're not really together. These are split here, and the anions and the cations are floated on separately, as they are in this picture right here. We'd have X negative, X negative. This X negative isn't part of the exchange. This is what's called a spectator ion. Now, in this case, if we were to write what's called an ionic equation, we would actually show these as being separate. Any actual dissolved solution would be separated. Zinc metal plus copper 2 plus nitrate yields zinc plus 2 plus NO3 minus plus copper metal. I want to balance it, I put it to here, and to here. This is less common, to be honest. It's not used very often. But the third one it's called a net ionic equation, would remove spectators. These guys right here are spectators. So it's going to be zinc metal plus copper 2 plus yields zinc 2 plus copper metal. Okay. Molecular, ionic, diionic. Now, balancing chemical reactions. Balancing simple chemical reactions. Type in here, let's go. Okay. I showed one example with the copper and the zinc. Let's do another one involving, let's say, silver and copper. Copper metal plus silver nitrate yields copper nitrate plus silver. No charge. Okay, this is a redox reaction. You could do the half reactions. Copper metal will go to copper plus 2 and 2 electrons. Positive, negative equals 0. Get a voltage on that guy. Silver plus goes to silver, no charge, plus, can't have electrons there, it's got to be on the other side, and we'll put it over here, plus 1 electron. Okay, so the balancing process we already actually did. Get a voltage on that guy. I'm just going to pop this down, grab my 2 voltages. Okay, so we have copper 2 plus 2 electrons gives me a 0.34 volts. Okay, this is a, and I should change it because I have the reverse reaction. Make sure I got that right. Copper 2 plus, okay, a negative 0.34 volts. Okay, negative 0.34 volts. So this guy doesn't want to give away 2 electrons. The question is, can the silver take it? Silver should be as is. There it is, and it's a positive 0.8 volts. Right, so positive 0.8 volts. So yes, this thing can and is willing to force the copper to give up 2 electrons because it's just going to take them. Add the 2 together, and we get a positive 0.46 volts. This reaction will run. Now, the balancing process is the last part here. This reaction is giving away 2 electrons. This one's picking them up. You should be able to draw a picture of this. We would have a beaker. Give myself a little room here. Being able to draw these is extremely important in the sense that if you can't draw it, you really don't know what you're doing here. So we'll just draw a little picture of this, and we have a piece of, this is a before picture, this is an after picture. So before, we have a stick of copper metal, and we have silver ions in here, Ag+, and I'm going to go a nitrate, just again floating around on its own, like that. Over the course of the reaction, every time 1 copper jumps off into solution, okay, and copper actually is blue, so this thing will be becoming a slight blue tint to it as the copper jumps off. 2 electrons have to be given away. Silver can only pick up 1 electron. So part of the balancing process is to balance the electrons. Whatever electrons on one side have to be gained and lost by the other. This goes times 2. Give me 2 electrons, 2 silvers. There we go. 2 of these guys will therefore jump onto the post, forming a solid lump of silver. I'm assuming, since there's lots of copper here, that this particular reaction will continue until the silver runs out. It will go to completion. You need to have a surface by which this reaction can take place. So even if there is no solid substance in the chemical reaction, you need a surface. That surface could be a unique metal that will not take part in the chemical reaction. Either way. Now, when I write out my overall reaction, then it's going to be 2Ag plus copper metal yields copper 2 plus 2Ag solid. This is the overall balanced chemical reaction. The process for a simple reaction of redox is like this, and it's quite straightforward. The rules for a more complicated redox reaction will be coming in a future videos. Again, that's also more along the lines of just simply following some directions. But I'll stop there. Thank you.